Hello everyone and welcome to the fifth lecture of this course, Fracture, Fatigue and Failure of Materials. So, in this class we will be discussing some more about the Griffith criterion, which we have introduced already in the last lecture, and from there we will also look into the drawbacks and the ways by which Griffith criteria has been modified to cater to larger kinds of materials, as Orowan's modification and finally Irwin's consideration. So, in the last class we have seen that how fracture strength of a materials can be determined. At the first hand, we have seen that how the theoretical strength of a materials are determined in case of a perfect lattice structure. Let us say we have atomic structure like this, which are perfect without any defect, and if we are applying tensile stresses on this, at some point fracture will initiate, and this fracture strength is known as a theoretical cohesive strength or theoretical fracture strength of a material, and that is related to the elastic modulus, the surface energy as well as the interatomic distance. So, let me write this term. E is the symbol for elastic modulus, and gamma S is known as the surface energy, whereas A0 is the interatomic distance. So, typically the theoretical fracture strength of a materials is related to the square root of E gamma S by A0, and in case there is a defect in a material, as we know that all the materials or components are supposed to have inherent defects in it, in that case Griffith has tried to find out the fracture strength of a material in case of an infinitely long and wide component having a center crack of total length 2a, and the fracture strength in such case is related to the square root of 2 E gamma S by pi a, where a is the new term here, different from what we have seen for the case of theoretical fracture strength, and this a represents half crack length. So, in case of fracture mechanics we often will use this term A, and it is different from A0, where A0 is the interatomic distance. So, this needs to be carefully considered. Okay, now, if we look into this Griffith criterion more carefully, we will see that if we are kind of putting the relation in such that sigma f root over pi a, that is equivalent to root 2 E gamma S. We are simply rearranging the equation. Now, for any material, elastic modulus as well as the surface energy are actually the inherent materials property of a material. So, in that sense we can see that this term on the left hand side, that is the sigma f root over pi a, is supposed to be a materials property, although we have also seen that fracture strength of a material is not a materials property. It is related to the crack length, and if we are varying the crack length, that means the fracture strength of a particular material or a component is supposed to change. On the other hand, if we are simply rearranging this relation and we are getting sigma f root over pi a, that is considered as a materials property, because this is related to none other than only the elastic modulus and the surface energy of a material. We will see later on that this factor here, sigma f root over pi a, is nothing but the fracture toughness of a materials. We will go through further details of that, but for now you should be carefully considering this term as the fracture toughness of a material, not fracture strength, rather the toughness of a material, which is combined of the fracture strength as well as the crack length of a material. So, let us now solve a problem related to fracture strength determined through Griffith criterion accordingly. A glass sheet has fracture strength of 50.6 MPa and the elastic modulus and surface energy are respectively 72 GPa and 0.3 joule per meter square respectively. So, that makes our sigma f as 50.6 into 10 to the power of 6 Pascal and elastic modulus of 72 into 10 to the power of 9 Pascal, whereas the surface energy is 0.3 Pascal meter. We have seen in the last problem that we have solved that joule per meter square can be converted to Pascal meter. Now, what we need to determine from here is the critical length of a surface or edge flaw that can trigger fracture. So, at the point of fracture, it has to maintain this Griffith criteria, which is sigma f equals to 2e gamma s by pi a. So, if we simply plug all the values here, 50.6 into 10 to the power of 6, and here comes 2 into 72 into 10 to the power of 9 into 0.3 divided by pi and a, and we can determine the critical crack length in that case. So, let us simply solve this problem. .6 into 10 to the power of 6, this will be equivalent to the right hand side here, so that comes as 117,264.6 into root over of 1 by a. So, that makes root a equivalent to 2.32 into 10 to the power of minus 3, or a will be just the square of that, which comes as 5.37 into 10 to the power of minus 6, and the unit of a in this case, since we have considered the unit of length as meter, so this should be a equals to 5.37 into 10 to the power of minus 6 meter, which is equivalent to 5.37 micrometer. So, a crack as small as 5.37 micrometer is sufficient to trigger fracture, and that leads to a fracture strength of 50 or 50.6 megapascal. So far we have seen that how through Griffith criterion the fracture strength of a material can be determined, and now is the time to look into if there are any drawbacks. The prime factor which is there for Griffith criterion is that this is suitable for only brittle materials with no plastic deformation, and there is another drawback of Griffith criterion which says that this is valid for only very sharp crack or almost infinitesimally small sharp crack. So, let us just see the first point and let us see how this has been modified. Griffith criterion has been modified to suit the need for large different categories of materials. So, ORO1 has particularly modified Griffith criterion, taking care of materials such as polymers or metals which have significant amount of plastic deformation prior to failure. So, for such cases Griffith criterion is being modified and the fracture energy in this case is several orders of magnitude greater than the surface energy. That is what has been realized, and Griffith criterion has been simply modified by adding the term gamma p here, where gamma p is nothing but the plastic deformation energy. So, we have seen that according to Griffith criterion, sigma or sigma f is given by simply 2E gamma s by pi a, and to that this gamma p term has been added to take care of the plastic deformation energy. So, if we are rearranging this equation, this can be done as sigma f equals to root over 2 e gamma s 1 plus gamma p by gamma s. We can simply write it in this way, just to make sure that the first part here is nothing but the stress, the fracture strength that is required as per the Griffith criterion. So, in that case we have another factor 1 plus gamma p by gamma s, which is what the modification done by OR1. But we also know that gamma p is typically much larger than the magnitude of the gamma s. So, in that case the term 1 which has been added here does not make much of a sense, because gamma p by gamma s will be a large number, and in that case 1 can typically be ignored, leaving us that sigma according to OR1's modification is 2 e gamma s by pi a. So, this is nothing but what originally Griffith has estimated, and with that we need to multiply it with gamma p by gamma s, this ratio of the plastic deformation energy to the surface energy of any material. Now, there is a drawback of Griffith criterion of this OR1's modification as well. So, this is based on the practical estimation of this gamma p. Now, gamma p is very difficult to measure experimentally. We can qualitatively analyze the plastic deformation energy, but it is very difficult to quantify this number or this value from the practical experiments, and that makes finding the sigma value as per OR1's modification quite critical if we are talking about experimental validation of this. Okay, so, we will see how this has been further modified, but before that let us focus on the second drawback of Griffith criterion, which says that it is valid for only very sharp crack. So, let us see that by sharp crack, again sharp is a qualitative term. We need to understand that how sharp the crack needs to be so that the Griffith criterion gets valid. So, for that we have to understand that the mechanism by which fracture occurs. So, according to Griffith criterion, we have seen that if we have a component which is infinitesimally long and wide with respect to the crack length, which makes the crack length as very small compared to the overall width of the specimen, right, and if we are applying tensile stress to it, fracture will occur as per this relation. Okay. Now, we are applying a stress sigma a, and at the point of fracture the sigma a will be equivalent to sigma f. But at the tip of the crack we are applying the sigma a as the overall stress, but at the tip of the crack, both these points here, we know that the stress gets maximized. So, sigma max actually gets sigma a into kT, where kT is the stress concentration factor, right. So, in any case, if the sigma max achieves the theoretical value for fracture strength sigma th, at that point only it gets sufficient energy to break the bonds here and to create new surfaces. So, that is the initiation point of fracture. So, this means that we need to find out the applied stress that is necessary to get the sigma max exceed or gets equivalent to the theoretical cohesive strength of a material, so that fracture can initiate. So, the theoretical cohesive strength, as we all know, is nothing but root over E gamma s by A0, and if we are using this relation here instead of sigma max, we can rewrite this equation as, okay, let me write this full equation here. E gamma s by A0, this is whole root over, and that is sigma A into kt, where kt is nothing but 2 root over A by rho. We can simply rearrange this relation to see what actually is sigma A. So, sigma A will be given by 1 by 2 E gamma s by A0 into rho by A. Again, if we are rearranging this relation so that it gets familiar with the Griffith criterion, this fracture strength related to Griffith criterion, we get something like this, 2 E gamma s by pi A, and since we are introducing this term pi here, we need to multiply that to balance. So, that gets pi rho by 8 A0. So, this is simply rearranging this relation here. Okay. So, all we can see is that this part is nothing but the fracture strength as per Griffith criterion, and it will be valid. So, this applied strength will be same as Griffith criterion only when this factor is equivalent to 1, right. So, this is what we are seeing here, rearranging this relation, and in case this term here gets equivalent to 1, we know that this entire thing will be as per the Griffith criterion. This is the sigma f as per Griffith criterion, as we are seeing here. So, that makes the condition to be valid to get Griffith criterion active is pi rho by 8 A0, that is equivalent to 1, which makes rho equals to 8 A0 by pi. So, this is nothing but the radius of curvature of the crack. So, that means the crack radii or the tip of the crack radii should have 8 A0 by pi, this or even lesser values. So, we know that A0, the interatomic distance, is sometimes on the order of angstrom. So, you can imagine that rho value should be really very sharp, of the order of a few atomic distances, so that Griffith criterion gets valid. Okay. So, now that we have seen that how Oravan has tried to modify the Griffith criterion, and we have also seen that in case Griffith criterion is modified to include the plastic deformation energy, we have also seen that there are some drawbacks of Griffith criterion as well, which says that the plastic deformation energy is very difficult to determine experimentally, and which calls for some other kind of modification, so that we do not need to determine the plastic work energy, but still can quantify the amount of stress that is required for fracture to initiate. And here comes the Irwin's consideration. So, what it says is something like this. So, there is a concept of a new factor which he has introduced, which is known as G, or also known as the strain energy release rate. So, this is the stored energy or the potential energy that is stored in a system or a component, and when we are applying stress and the crack is growing, that leads to fracture, there is this elastic energy is being released over some volume. We have also seen that, and that is equivalent to the total energy related to the surface energy as well as the plastic deformation energy. So, this entire the way Oravan has modified this. So, this is how Oravan has modified Griffith criterion. Oravan's modification of Griffith criterion says that fracture strength is not only related to surface energy, but it should be related to the plastic work energy as well. And we have also seen that this plastic energy actually is quite high a number, which should not be ignored. In case of ductile materials, plastic deformation energy should not be ignored, or if we do that, that can lead to some discrepancy in the estimated values. So, Irwin has moved a step forward and he considered this entire thing to gamma s plus gamma p as nothing but the G, the strain energy that is being released per unit advancement of the crack. Okay. So, in that case, if we are considering that, the sigma is then sigma as per the Griffith criterion or as per Orovant's modification is then turning to sigma f equals to root over E g by pi a. So, this elastic energy or the strain energy release rate is actually equivalent to del u by del a, where u is nothing but the potential energy or the elastic energy that is being released per unit growth of the crack, and this says unit crack growth. So, rate in case of fracture mechanics has a significance, because in case of when we consider anything as rate instead of the time, what we mean here is the growth of the crack. So, per unit growth of the crack, how much is the change in the elastic energy, that is considered as the strain energy release rate, and that will lead us to the fracture strength of a material. In case we know G, we also are supposed to know the E and the A, so that we can determine the fracture strength of a material. So, this leads to the conclusion for this part of this lecture, which says that Griffith criterion is valid only for brittle materials and for infinitesimally sharp crack, and that Orovant has modified the Griffith criterion to make it suitable for the behavior of ductile materials, particularly metals and polymers, for which there are significant amount of plastic deformation or ductile deformation, and that calls for the plastic work energy, which typically is much higher than the surface energy of a material, and in case of ductile materials, this plastic work energy should not be or cannot be ignored and should be included in the relation. However, we have also seen that from this modification that this plastic work energy is very difficult to determine quantitatively through an experiment, and here comes the modification by Irwin, who introduced the term strain energy release rate, and that is equivalent to the overall surface as well as the plastic work energy, which is given by the energy that is being released as the crack is growing. So, these are the following references that has been used for this part of this lecture, and thank you very much for your attention.